Hi everyone. Today we will start a new topic. So the new topic is rotating machines. So until now in our class we discussed the reviewed the AC power. We discussed the basic three-phase circuits and power measurements, and then we discussed the electromagnetic circuits. After that, we started applying the magnetic circuits on transformer, and we discussed the single phase and three-phase transformer. So all of these are still stationary circuits. What about the rotational or any electromechanical device? So this is going to be the remaining part in our course. So we will start today defining the rotating machines, what the meaning of rotating machines, what are the different types of rotating machines that we are going to discuss in our class. So the objectives, as you can see, understand the meaning of electromechanical energy. So what is the concept of electromechanical energy conversion, and recognizing the importance of magnetic field in the energy conversion. So we have electrical energy and mechanical energy. What is the role of the magnetic field to make this kind of conversion between electrical to mechanical or mechanical to electrical? And recognize the motoring and generating actions of electrical machines, and knowing the different types of electrical machines that will be discussed in our class. So starting from the concept of electromagnetic conversion. Let me have my laser. So an electric machine is a link between an electrical system and mechanical system. So if you have electrical system, like our supply, and a mechanical system, something need to be moved, the link between both is called the electrical machine. So this is called electrical machine or electromechanical device. So electrical machine is one of the electromechanical device systems. So if the conversion from mechanical to electrical, so moving the energy from electrical side, from mechanical side to electrical side, so this is going to be a generator. So the generator can convert mechanical power into electrical power. So the energy flow from mechanical system to electrical system is called generating action. And the device that will convert mechanical power into electrical power is called generator. And if the conversion is from electrical to mechanical, so in the opposite direction, the machine is said to act as a motor. So the motoring action is nothing but converting electrical power to mechanical power. So the question is, does this mean that the electrical machine can work as both motor or generator if we reverse the power flow? So the answer is yes. So if you can reverse the power flow in the electrical machine, it can convert the machine from motor to generator. So the motor or generator, it's not like a separate machine. It's just a mode of operation of the electrical machine. So the electrical machine itself can act as a motor or as a generator, depends on the power flow direction. So conversion of energy is based on two electromagnetic phenomena. What are these two phenomena? First one is when a conductor moves in a magnetic field. So conductor moves means you have a source of mechanical power, which is going to move this conductor. Conductor means any carrying current conductor, any wire. So if this conductor moves in a magnetic field, voltage is induced in the inductor. So voltage is going to be induced in the inductor. This means we generated volt. So this is a generating action. So the generating action will depend on moving a certain conductor material or conductor in a magnetic field. Let's see the other opposite action or phenomena. When a current carrying conductor, now we have a current carrying conductor, which means there is current flowing in this conductor, which means we have a source of electricity. So when a current carrying conductor is placed in a magnetic field, the conductor experiences a mechanical force. So experience a mechanical force, this means we generated mechanical power. So this can be considered as the motoring action. Comparing these two phenomena together, guys, you will find that the magnetic field is a key factor in both of conversions. So as you can see in the first action here, we have magnetic field. So here the conductor is moving in a magnetic field, and in the other action here you have the carrying current conductor is placed in a magnetic field. So magnetic field is a common thing between the two conversions, and this is actually the idea of any electromechanical energy conversion. If you would like to convert electrical to mechanical or mechanical to electrical power, you have to have a source of magnetic field. This doesn't mean that the magnetic field will consume a lot of power from your system. However, it's essential to convert the power from a shape to another shape. We will see this in more deep and more details in the different machines we will discuss in our class. And you have to consider that there is no way to convert electrical power to mechanical power or mechanical to electrical power without having a magnetic field. So this is a key factor of the electromechanical energy conversion. In order to do that, guys, and understanding the concept of generator and motor, let's just remember the basics of electromagnetic. So firstly, let's remember together the electromagnetic force. So for the current carrying conductor, if you have current carrying conductor, so you have a conductor, this is our conductor here, a wire, and you have a certain current flowing in this wire in this direction. And this wire, this carrying conductor, the force known as Lorentz force produced on the conductor is, so the force that will be produced across this conductor is LIB. What are these terms? L is referring to the length of this conductor. I is the current flowing in this conductor. And finally, B is the magnetic field density that are applied to this conductor. So this is the force that will be applied to a conductor if we have this conductor carrying current in a magnetic field. Okay, so this is called Lorentz force. So here, guys, in Lorentz force, this is gonna be the action of motoring now, because we have a source of electricity that already flow inside this inductor, which means we have already a source of electricity, we have electrical power, and mechanical force will be generated. So this is nothing but the motoring action. So the motoring action is depending on this rule. And let's see the opposite action, which is the generating action. So we have what's called motional voltage. So what is the motional volt? If a conductor of length L moves in a linear speed V, so moves, guys, means you have a source of mechanical power that will move our conductor. And here it moves in a linear speed V, so this is not rotational motion, this is linear motion or translational motion. So in this case, in a magnetic field B, so we have to have the magnetic field also. So we have a certain magnetic field density B. So what will happen? There will be an induced voltage that will be generated across this conductor. What is the relation of this volt? So the volt is BLV. B is the same magnetic flux density, L is the conductor length, and V is the speed of this conductor. So this is the generating action relation. Based on these two actions, guys, all of electrical machines are going to work. So since we are going to discuss mainly the rotating machines, not linear machines, so we have in our life, we have both linear machines and rotating machines. However, the rotating machines are much used in our industry, so we are going to focus on the rotating machines. So let's see together the basic structure of the rotating machines. So structure, this means we are referring to the mechanical parts that we have in our machines. So we will see the mechanical parts, and later on we will see also the electrical systems or electrical parts that we would have in our machines. So firstly, referring to the structure or the mechanical structure, we have two major components. What are these two major components? One component is not rotating, so it's stationary component, and we will call it stator. And the other structure is a moving structure, which is going to rotate, and we will call it rotor. So we have two main structures, rotor and stator. So in order to have a motion between the two bodies, so this is the internal body of the rotor, and this is the external body of the stator. In order to have this type of motion, you have to have a space in between. Otherwise, these two structures will be collapsed together. Okay, so we shouldn't have any kind of friction or any kind of like objection between the two bodies. So we have to have a space in between. This space, guys, is called air gap. So no electrical machine without air gap. So all of electrical machines, we have an air gap between the two structures, the stator and the rotor. Okay. So again, the stator is this part of the machine doesn't move, and normally is the outer frame. Sometimes, guys, it could be the inner frame. It depends on the application. For instance, the inner frame of the ceiling fan is the stationary frame, and the outer frame is the rotating frame. So in this case, the inner frame is going to be stator and the outer frame is rotor. But most probably in most of the machines, you will find that the inner is a rotating object and the outer is the stationary object. So in general, we can say that stator is the part of the electrical machine that doesn't move and normally is the outer frame of the machine. And the outer frame of the machine, guys, will be like having what's called yoke. So this yoke is the stationary part in the bottom here that will be used as the base of this machine. Okay, so this is called stator. And the other part inside here, we call it rotor. So this part of the machine is free to move and normally is the inner part of the machine. So we may have this shape, guys. We may have different shapes, and we will compare between them in some of the machines. Okay, so here, guys, we have what's called when you see that in practical with the dimensions, so you will see like you have like constant air gap between the stator and rotor structures. So this is called cylindrical type. And here you will have different air gaps between the horizontal and vertical axes. And in this case, we call that the air gap is not uniform or non-uniform air gap. And in this case, we call this machine a salient pool machine. we will see all of these guys in the different types of machines we will discuss in our classes. Okay, so we may have uniform air gap and we may have non-uniform air gap. Okay, so the uniform air gap we call the machine cylindrical machine, and the non-uniform air gap we call the machine as Cillian tool machine. How can we make these types of machines, guys? So whatever stator or rotor, both will be made of a ferromagnetic material. Ferromagnetic material means it's electromag. So once we have some electrical wires or wires connected around these magnetic materials or ferromagnetic materials, a flux will start moving in these ferromagnetic materials. So these ferromagnetic materials, guys, we discussed the magnetic circuits before, and we could see the different magnetic materials. Okay, and how can we create the different structures? So we bring the different magnetic material in sheets, not in cores. Why? Why we do prefer to have the machine made of slices or sheets? Because as you remember, when we discussed the core loss, we mentioned that we have what's called eddy current loss. So the eddy current loss can be reduced by creating our core from sheets, not from a complex or a complete core. Okay, so this will reduce the eddy current in our machine. So if we have a sheet, and for sure this sheet will have insulation, so insulation just from one side, okay, and we call it laminated sheets. So these laminated sheets, guys, if we have the sheet and start bunching the sheet from inside and having here the slots inside, so this now will represent the stator sheet. So this is one sheet of the stator right now. And the inner part that we bunched out from this structure, which is going to be here, will have also some slots like that. And these slots, we call it outer slots, but these are inner slots. So inner slots in the stator to insert the windings of the stator. And here we have outer slots to insert the rotor windings. Okay. Here in the middle, we will have the space for our shaft. So here inside, this will be the shaft place. So in order to have a rotating part, so this rotating part, so this is a section of the machine. When we collect like hundreds of these sheets together, so in the middle here, we will insert a shaft. This shaft bar will be supported by what's called bearings in order to allow our machine to rotate with minimum friction. Okay, and we will see some more detail about the structure of a complete motor in few slides. So this is how we make our machines. So we have the ferromagnetic material. We use sheets, laminated sheets of ferromagnetic material, and these sheets are insulated from one of the sides just to reduce the cost of the insulation. Okay, and at the same time, we guarantee to reduce the eddy current loss inside our machine. The conductors placed in the slots of the stator or the rotor are interconnected to form windings. So inside these slots, guys, we will have some wires. These wires will be connected together to form what's called winding. So by the end, we will have stator windings and rotor windings. The winding in which voltage is induced is called armature winding. So we will have in our machine, guys, we will have one of the windings will be responsible of the power of the machine, of the electrical power of the machine. This winding is called armature winding. So all of the time, the armature winding are referring to the power carrying winding of the machine. Why? Because as we mentioned before, we will have another type of winding that carry the magnetic field or the source of field that will allow the machine to convert the power from electrical to mechanical or mechanical to electrical power. So we will have field winding and armature winding. So the armature winding are the power winding, but the field winding will have very small amount of power, as we will see in the different types of machines. The winding through which a current is passed to produce the primary source of flux in the machine is called the field winding. So as we mentioned, now we have the armature winding, which are going to be responsible for the power, and the other winding will be responsible for creating the magnetic field in our machine. Sometimes we may not have this type of field winding, but we should provide another source of magnetic field, which is going to be now permanent magnet. So we can have source of magnetic field either from permanent magnet or from field supplied by some electrical sources. So we can have the two types. Okay, so these are the two types of field machines, or how to make the field inside a machine. Rotating electrical machines takes many forms and are known by many names. We will have a lot of AC and DC machines. We will have special machines. We have what's called induction. We have synchronous machine. We have permanent magnet machine. So we will have a lot of types of machine, depend on how the machine is formed. The three basic and common ones are DC machines, induction machines, and synchronous machines. And these are the three types that will be discussed in our classes. There are other machines such as permanent magnet machines. We are not going to consider this in our classes, but these permanent magnet machines are used a lot, by the way, in industry, but it's not like suitable for the undergrad level. So we can discuss that for master's degree or PhD degree. Okay. Some other machines that can be discussed in undergrad level, like special machines, like stepper machine, for instance, like universal machine. But because of the time limitation, you have only one course of electromechanical devices. You cannot discuss all of the machine types. However, in some other programs, guys, for more deep electrical power departments, they have more machine courses, and in this case, they may discuss the different types of machines like stepper machine, like universal machines, and some other special machines. So these are the different types of machines that you may find in industry. Returning back to the motoring and generating action, guys. So the electrical system makes current flow through the conductors that are placed in the magnetic field. So this is in motor. So you will have a source of electricity that produce the magnetic field. A force is produced on each conductor. So every conductor will have a certain force applied on it because of the motoring action. If the conductors are placed on a structure free to rotate, an electromagnetic torque will be produced. So if you can imagine with me, guys, if this is a rotating object and you have a conductor here and the other conductor in the opposite side, so if the current is going inside the page like dot and coming out of the page like that, so in this case, you will have a certain force applied to this direction and the force will be in the opposite direction like that. So between the two conductors, you will have a distance d, and in this case, the torque will be F, this force times distance d. Okay, so this is how to interpret the linear to translational, to rotational force. So the linear force is called force, and once we have a rotation now, this will produce what's called torque. Okay, so this is the motoring action. And the opposite for the generating action, if conductors rotate in a magnetic field, a voltage will also be induced in each conductor. And you know, all conductors are going to be connected together to form windings. So The rotating structure, which is rotor, is driven by prime mover. Prime mover is something that makes the motion or generate our machine by mechanical power. So, like for instance, in generators in power plants, this can be turbine, for instance, like wind turbine, like steam turbine, and all other turbines used in our power plants. Okay, so these are called prime movers, which are providing the mechanical power to our machines. A voltage will be induced in the conductors that are rotating with the rotor, and if electrical load is connected, so once we have voltage applied or voltage generated, voltage generated from the magnetic field and motion action. So once we have magnetic field and mechanical power to provide rotation for our machine, so you will have generated voltage. Once you have a load connected to this winding that has already some voltage generating on it, so you can start supplying electrical power. So if an electrical load is connected to the winding formed by these conductors, a current I, so the current I, the symbol of current is I, will flow, delivering electrical power to the load. Okay, so this is nothing but the generating action, guys. Moreover, the current flow through the conductor will interact with the magnetic field. So since we have generated current, any current flowing in a conductor, guys, will have some magnetic field around this conductor. So you will have now two different fields, a field that generated the electricity and a field from the generated current. So these two fields will produce what's called reaction. So we will have a reaction. So this reaction will produce a torque in order to tend to oppose the torque applied by the prime mover in order to reduce the amount of output power. And we will see some solutions for these problems in our machines, like in DC machine, for instance. Okay, so we have what's called armature reaction. Armature reaction. We will see this armature reaction in DC machine and in other machines as well, and we'll discuss it in more detail. Here is, guys, one of the machines that we will discuss in deep in our class, which is DC machine. So the DC machine will have the armature winding on the rotor side. So the power winding on DC machines are placed on the rotor side. So this is the power winding. And the stator is the outer structure, as you can see. Here we have an electromagnet. So we have wires coming here on these magnets producing a north and south poles. So the flux is going to flow from north to south like that and will cut the rotating object inside, which is carrying already the windings of the machine in order to generate electricity. And this is going to be the generating action. The opposite action is when you supply the inner structure here by electricity, a current will flow in the windings, which will be on the top of the structure of our rotor. And in this case, you will have a magnetic field and you have a current carrying conductor. So this will apply a force on every conductor and causing the machine to rotate to make the motor action. One can ask here, this is now a rotating part, how we will connect the electricity? So actually this is through these elements here, which are brushes. So we will discuss this in more deep when we start discussing the DC machine. So in DC machines, we have something called commutator and brushes. And these brushes are used to transfer the electricity to the rotating windings of the rotor. So this is the DC machine structure. Also, we have induction machine. In the induction machine, guys, we have stator winding and serve as both armature winding and field winding together. How this comes? This is actually because this machine will have what's called self-induction. Why we have self-induction in induction machine? So we will discuss the operation of the induction machine in more deep, and you will understand how this machine is self-induced the volt in order to start up the machine. And for that, we call this machine as induction machine. So you don't need field winding for this type of machines. This is in motoring action. In generating action, in order to provide electricity, you have to have a source of magnetic field, and this can be like generated by external auxiliary devices, and this is an induction generator, but induction generator is not going to be considered in our class. We may just give you the flavor, what the meaning of induction generator and where we can find it in our life. So you can find induction generator, for instance, in wind energy systems, and they have like two different shapes, what's called doubly fed induction generator. They have what's called self-excited induction generator. However, for induction machine, this is the majority of machines or induction machine type used in industry, and we'll focus on the induction machine as a motor, not as a generator. Okay, so this is called the induction machine. Here we have the shape of these type of machines, guys. So this is, for instance, the internal rotor of the machine. We have here the windings of the machine, and here we have what's called the slip rings. These windings are going to be soldered on these slip rings, and we will have some external brushes to connect these rings outside of the motor. So this is called wound rotor type. And we have another well-known configuration is called squirrel cage. So the squirrel cage is used a lot compared to the wound rotor type, and we don't have any kind of windings. It's just some bars like that or cage like that, and this will act as a rotor winding, and this will also allow the induction motor to operate. The third type of the machines is the synchronous machine, and this is widely used in power plants as generators. So the synchronous machine, we have what's called salient pole machine. We have what's called cylindrical type machines. You will find the comparison, we have it in our classes, the difference between these two machines and where we can find the salient pole machines and where we can find the cylindrical type. And as you can see here, we have the rotor structure inside the machine, and here is the stator structure and stator windings, and this is here like a relatively big synchronous machine here, including the rotor and the stator in this photo. Okay, so in this type of machines, guys, we have actually two windings. So the windings on the rotor side will be the field winding, and this will be supplied by a DC source to produce our magnetic field, but the power is going to be very small on these windings, and the majority of power will be on the armature winding, which are located inside the stator slots right here, and this will generate the electricity or will be connected to our loads after that. Okay, so this is the shape of the synchronous machine. So this is a summary for what we have described right now, the different types of machines, the phenomena of the energy conversion system, the importance of magnetic field and the energy conversion system, the motoring and generating action concept, and the different types of machines. We're going to continue discussing, guys. We still have some time, so I'm going to continue in the next material, which is starting in the DC principles or principle of DC machine operation. So the objectives of this part of DC machines, this is going to be the remaining part of the DC machines, guys. So we will discuss a lot of things in the DC machines. So we need to know the construction. So we already knew that we have now rotor and stator, but we are going to discuss more in deep what are the main parts of the DC motors and how we can construct and how we can connect these windings to outside, understand the operation of the DC machine, understand the commutator, so what the meaning of commutator and the brushes in a DC machine, recognize the different winding types of the DC machine, so how can we connect the DC machine windings? We have a lot of connections, and drive the developed torque and the developed voltage of a DC machine, and discuss the different types of DC machines. So this is going to be the objectives of this material. Starting firstly, guys, from the DC machines. So we are still having DC machines in industry, guys, most probably in the applications that require a constant speed. So in industry, you will find what's called variable speed drives and fixed speed drives. So fixed speed drives, we do prefer to use DC motors, and variable speed drives, we do prefer to use AC motors. So where we can find the DC motors in industry, for instance, you can find it in the applications of solar energy. So most of the solar energy applications that generate electricity by means of sun power, like heliostat, like linear Fresnel, like two other types of solar energy systems or topologies. So all of these topologies are using the DC motor in order to make what's called solar tracking system. So this is gonna provide a motor with tracking system to track the sunbeams all of the time with what's called actuators using DC motors. So we do prefer to have it or to have DC machines in these type of applications. So the DC machines are versatile and extensively used in industry. A wide variety of volt ampere torque speed characteristics can be obtained from various or connections of these field windings. So we will have what's called separately excited, we will have what's called shunt winding, we will have what's called series winding. So this is nothing but the connection between field winding and armature windings. Although a DC machine can operate as either a generator or motor, at present its use as a generator is limited because of the wide speed of the AC power, and also, guys, because of using the power electronics. So by using power electronics, it's very easy to have DC from AC supply using what's called rectifier. So we don't need DC generators anymore. So we can say that DC generators are obsolete. It's not used anymore in industry because it's very easy to have the DC power from power electronics that has the name of rectifiers. So rectifiers can convert AC power to DC power and use it in industry. So this is much better than having DC generator in terms of efficiency, in terms of size and everything. The DC machine is extensively used as a motor in industry because, as you know now, as we discussed, power electronics solve the problem of having DC source. Its speed can be controlled over a wide range of relative ease. Why, guys? Because the relation between torque and speed is linear. So this is or speed and volt or torque and current. So the linearity of the speed control of DC motor makes it much easier compared to other control. Large DC motors in tens of or hundreds of horsepower are used in machine tools, printing process or presses, conveyors, fans, pumps, hoist, cranes, paper mills, textile mills, rolling mills, and so forth. So mainly, guys, for large torque applications. So if we need very large torque, we use DC machine. So we don't prefer to use AC machine for very large torque. DC machine is much better in large torque, especially series DC motors. Okay, this is thanks to the characteristic of the high starting torque of the DC series motors. Okay. Additionally, DC motors still dominant as traction motors used in transit cars and locomotives cars as well. So this is also one more application for the DC machine. Small DC machines, guys, can be found in industry in fractional horsepower. So you can find very small ratings DC machines. You can find it in the toys of kids. So it can make the very easy small motors using DC machines. However, it's not that easy to make it with AC machines because AC machine needs AC supply, and small devices like toys are just working with battery, which needs very small amount of power and small volts. So in this case, we can use very small horsepower ratings DC machines. Okay. So these type of small rating machines are used primarily as control devices, such as tacho generators. So we can use it also in control, like tacho generator. So tacho generator, guys, is providing volt according to the speed. So it's kind of measuring the speed by interpreting the speed to volt. So this is called tacho generator. So it's used a lot in controls and also in servo motors. So servo motors are also used a lot in control systems. Okay. So servo motors, we have in industry what's called DC servo motors. We have what's called AC servo motor. So DC servo motor is a DC machine. AC servo motor is a two-phase induction machine. So we use actually the servo motor a lot in industry as a DC servo motor system. So this is also used for positioning and tracking control, as we mentioned, for solar tracking, for instance. The DC machine definitely plays an important role in industry. So this is regarding the introduction, guys, of the DC machine. So let me see if this video is working right here. So I'm not sure if the computer sound is included or not. Okay, let me check that. Just a moment. So guys, I'm not sure if this is possible to be considered, or you can hear it in the recording class or not. So in this case, I urge all of you guys to just click this link and see the video, and I'm gonna demonstrate that with you right here in our class. So now, if we have the configuration of our winding like that. So here we have our winding starting from this point, for instance, going to A, B, C, D, and return back again. So this is gonna be inserted here inside. Okay. Now, if we connect the positive supply here and the negative supply here, and as you can see, we have here permanent magnets north and south, which means our magnetic field now is flowing from north to south like that. So what will happen is when we have a supply, the current will start flowing in our conductor. Okay. In case of the motor action. So in this case, in case of motor action, you will have a current flowing in the conductors, and the flux will cut this carrying conductor. So what will happen is, assume that we have a current direction like that. So this is the direction of current here, guys. Okay. So if a current is flowing like that here, so you will have a flux moving around this conductor. So this flux moving around this conductor will be in this direction, which means from the top side, the direction of flux will be in the opposite direction of the flux coming from north to south. And from the bottom side is going to be in the same direction of the flux coming from north to south. And here, since the current is flowing in this direction, so it will be in the opposite direction from the other side. So this will allow the motor to make a force for this conductor here, down like that, and here is going to be top like that. And this will allow the motor to start rotate in this direction. So this is the concept of rotation now. Okay, and you will see that more in deep in this video here, guys. Okay, so this is the rotating action. The generating action is the opposite. So if you have this winding moving already in this direction, and you have a flux coming in this direction, so this flux will cut the rotating winding and produce an induced voltage. So this EDC will be generated with this polarity, as you can see here, and will provide plus minus across this coil. How the volt will be collected to the outside terminal? So we will have what's called the commutator. So you will see in the video that you have a half cylinder. So this half cylinder will be connected or will be connecting the windings to the brushes. And once you rotate from the under pole, the north pole to the south pole, so this will be reversed in order to allow the half cylinder or the brush to have the same polarity all of the time. So the winding itself will see different polarity when the half cylinder changes with the brush, but the brush will have the same polarity all of the time. So we can say that the commutator plus brushes act as rectifier, which converts AC to DC. So this is the action that the commutator and the brushes are doing. Okay, guys? So please see this video, and we will continue discussing this part in the next class. Thank you so much, and see you in the next class.